Hello guys, today we are going to study about the 2 degree of freedom vibration analysis for the quarter car model. As you can see here, uh, we have a quarter car model in which we see the quarter mass of the car, and then we have the unsprung mass, which actually represents the mass of the wheel, and then this is actually getting the excitation in the form of the road profile from the bottom. So on the left, we see an actual system, and on the right side, we have the model representing this problem. So M1 represent the sprung mass, M2 represent the unsprung mass, and from the bottom, we see the input coming from the road profile in the form of a U. So K1 and C1 actually represent the system parameter for the suspension system, which is present between the wheel and the mass of the car, where the K2 and the C2, they are the spring stiffness and the coefficient of damping for the tire material. So actually I have chosen those property from some references. We will be modeling those values. So the mass for the sprung mass is 430 kg. For the unsprung mass, it is 40 kg. The coefficient of damping for the C1 and C2 are also given in the table as to be 4,000 and 3,000 respectively. Similarly, we can use the suspension stiffness and the tire stiffness given any numerical value. And for the model, we also need to have some road profile, some information in the form of some input. And we can also take the mathematical derivative of this function because we will be having forces in the form of uh, which will be developed in the damping. So the damping actually needs to calculate the velocity of the road profile. So the relative velocity will be used for the forces in the damping. Uh, so here, if we consider M1 and M2 one by one, then we can actually derive this equation, which represents the dynamics of this M1. So we have mass M1 times Z1 double dot. It's the inertial force. And plus we have a C1, which is being multiplied with the relative velocity. So the relative velocity for this one is Z1 dot minus Z2 dot. Similarly, K1 is being multiplied with the relative position vector, which represent the relative displacement between the M1 and M2. So the relative position becomes Z1 minus Z2. So these are the only two forces acting on the M1 which cause the vibration. If we consider M2, then certainly it is connected with all the component, including two springs and two damping. So the terms which are positive for the M1 will have the negative terms when it comes to the M2. So that is why this one should be negative, because this is the same magnitude of force but opposite in direction when it is linked with this M2. So other than those two, we also have C2 and K2. So for the C2, the relative velocity vector is Z2 dot minus U. And similarly, for the K2, it's Z2 minus U. So those two are actually the original equation. In order to model these two equations, we actually have to manipulate them. So from this equation, if we bring everything to the right except that z double dot, then the same equation give us this uh, values, which is actually, it depends upon the force developed in the damper and the force developed in the spring divided by the mass. We can take the integral of this signal to get the velocity of the mass. We can take the integral of the same and this signal one more time to get the position of mass with respect to time. Similarly, from the second equation, we can also get the acceleration. If we manipulate them, we take all the term to the right and we just leave the z2 double dot on the left. So those are the two equations that we need to model in the Simulink. And we can also think for if we put all the numerical values in the equation. So this is the equation. There's two equation actually results. I have shown all the parameter on this figure. M1, M2, K1, K2, C1, C2. And those three lines are actually the reference line about which those this M1 will be at equilibrium on this line, this M2 will be an equilibrium on this line, and this is the road profile when there will be no input. So whenever there will be some input coming from the road bump, so M1 and M2 will move. So just to show you some behavior, let's see if we apply this bottom as the input. So from this second reference line, this red line will move like this and the blue line will move like this. So it will actually have show some dynamic if we provide any input from the road profile. And the system will actually try to reach again its mean point. So it's now time to model this. So I have a blank Simulink model, and then I'm going to choose this first equation here, this one, and this one, those two values, in order to model those. So let me place them so that I can refer to those two equations easily and will take help from those two equations. So let me go back to my blank model. In order to model this equation, we need to take some common factors from the Simulink library. So some commonly used block that is actually frequently used is we may use gain block, we may have some constant, we may use some demux, and other than this, we can get from math operation, we can take this addition, and from the continuous uh, model, we can also take the derivative function and we can take this integrator function. Now, just to represent this first equation, um, so what I'm going to do is I just take this signal as, let's say I have a signal which is this one, and this is Z1 double dot. If I have Z1 double dot, I can actually integrate this signal two times in order to get uh, so if this is Z1 double dot, this one is Z1 dot, and this signal is then Z1. So if we think in this way, then how can we take this Z1 double dot we can get some signal, some two forces here, some two signals, and then divide this with M1. So this means that I can make this signal out of summing up two signal and then divided it by 1 over m. So 1 divided by m1. M1 is actually the numerical value of m1 is 430. And then actually this system is coming from the two sources, two forces. So I can just connect those two forces, and both of those forces are negative. So I can just put this minus minus sign here. Now, in order to get this force, uh, I do have the information about Z1 dot and Z2 dot, Z1 and Z1 dot. Still, I need to find Z2 dot and Z2. So in order to do this, I just need to copy this figure and make a copy like this one. And then now it has become Z2 double dot, and this has become Z2 dot, and this is Z2. Now I can actually go to this block one more time. I can actually put Control and I to invert it, and I can take this Z1 minus Z2, and then I can multiply with again. I can also invert this by Control I invert this, and I can use the K1 value here, which is 12,000. So this has become actually this force. This is what I need to make. So K1 times Z1 minus Z2. So this is the force that I have made of different combination from of different signal, and then I can take this and connect it here. Similarly, I can copy this and place it here, and instead of Z1 and Z2, I can just connect this Z1 dot minus Z2 dot. So actually this should be Z1 minus Z2. So I need to change the sign to plus minus here. And same is the case here. So I should write here plus minus, and then multiply this with C1, and C1 is 4,000. And then I can connect it here. So this completes the first loop, and let me rename this as C1 and this block as K1. So those two forces are negative for this mass, and as we discussed, it should be with a different sign, the opposite sign for the next one. So this means for the M2, there are four forces. So I have to change this two signal to plus, plus, minus, minus, and then enter. And then can I reposition a bit? And those two forces, I can simply connect with so those two forces have different sign for M1 and for M2. And this should be 1 divided by M1 divided by M2, where M2 is 40. So I need to change this value to 40. So this is M2. Uh, And then those two signals are actually what? So we can see from here, we have for Z2 dot, we have dealt with the first two, this term and this term. They are already done because they were readily available from the previous equation. We also need to know how to evaluate this one. So C2 should be negative, and it's the difference between the road velocity and the road profile velocity and the input velocity. This means that I can simply have a road profile parameter. So let's, for the sake of some discussion, let's say that I go to some source and then choose some road profile. Let's say this is the road profile. I invert this. Control I invert this, and I can also take the derivative of this one. So instead of this one, let me make a step function for the source. So source, I can choose a step input. I can control invert it. Control invert. And then I can simply add them like this one. Plus plus. I need to see a combination of those two step function in order to get some row profile input. So let me use a step time of 3 seconds, and the initial value is 0 and the final value is 0.01. And for the next one, the initial value is 0 at 4 seconds, and it will change to minus 0.01. So this will actually produce a step input, and then we can take the derivative of this block. So for continuous function, I can take the derivative of this one. So now I have the road profile and the road profile uh, velocity both at the same time. Now, once we have this, I can simply uh, make a copy of those two, and in order to get the force, I need to calculate Z2 minus U, and that's the U, and multiply this with K2. The value of K2 is 6,000, and then embed this force into the system. Similarly, I can choose the same technique in order to get the velocity of Z2 minus this derivative, which is actually the velocity of this row profile, multiply this with C2, and the value of C2 is 3,000. And then I can use this one. So now actually we have this as the dynamics of M1, and this is the dynamics of M2. This one is M2. It depends upon the 4 forces, and M1 depends upon the 2 forces. And finally, we need to plot the result. So what result do we need? Actually, we need to plot the signal that we are interested in. So if I go to the sync and take scope, so I would like to display Z1 as a function of time, and this signal is available here. Similarly, I make a copy and it changed to Z2, and that's the Z2. Maybe I am also interested in the road profile that I have generated. So let me call this as U. And similarly, we can also show all those three signal on the same scope because we need to compare them sometime. So I can see comparison, and this comparison will actually get this road profile data, the data for M2, the data for M1. And so we have all the system parameter, we have coupled those equation, and if we double click this scope and we run this simulation, so we get this result actually. So this orange line is the input, and then we have further two lines in the form of x1 and x2, just to bring the reference values to the of all the three signals to slightly different magnitude. What I'm going to do is I'm just adding some value with this signal so that it becomes slightly higher than the road input. What is do I need by this is actually if we consider this and this one, so the mean point are actually have some distance, right? So we can think that we have some distance between this M2 and M2, M1 and M2, and similarly M2 and ground. So in order to make for this arrangement, I can actually add, let's say, some numerical value with this one. So if I add, let's say, here with this one, I'm going to delete this. I'm going to change this into plus plus and add some numerical value, let's say 0.005, and then use it here. Similarly, if I use the same technique for this third signal and add a bit higher values, double up this with this signal, and now do the simulation. So instead of this signal, you see the reference line will slightly change. So this means now we can see the dynamics. The orange line is the input from the road. The blue one is actually the position of M2 with respect to time. And the yellow one is the position of M1 with respect to time. So this is the model. You can change any value. For example, in real time, you can increase the mass of the M1, you can increase the mass of M2, you can change the stiffness, you can actually change the magnitude of the step input and whatever you want to see. And so the result will actually be shown. So this is just a simple model of how you build a quarter car model for the analysis of 2 degree of freedom vibrating system when the input is coming from the road profile. So, and this is what actually uh, is the summary of this system. We have modeled the 2 degree of freedom system for those values, and finally we see the result in the form of the position. We can also see the inertia, inertial forces, and the velocity for all the masses if you are looking into this. So this concludes our this online lecture. So thank you for watching. I hope you learned from this. Thank you.